Dzień dobry. My name is Stephen Brobst, and I'll be presenting this morning on the fourth dimension of analytics. In the 21st century, in Silicon Valley, we have this saying, there are only three choices in the new economy. Either a company is already a data company, will soon become a data company, or will be extinct. Those are the only three choices. Data is the center of doing business in the digitally transformed economy. And what I'm going to talk to you about today is the evolution that's taking place into the next dimension of analytics. If we look at the history of analytics, thousands of years ago, discovery was based on empirical observations of natural phenomena. So mathematicians and scientists would use observations to confirm or refute hypotheses. They'd watch things and they'd get some ideas, and then they would use observations to deny or confirm what they were believing. A good example of is Nicholas Copernicus, a famous Polish mathematician. He went to university in Krakow, and he was quite famous for asserting that the Earth rotates around the sun rather than placing the Earth at the center of the universe. So prior to sort of his observations, people thought the Earth was the center of the universe, but mathematically he showed that the observations really weren't making sense relative to the hypothesis that Earth was at the center of the universe. So then he proposed that really it was the sun that was the center of the universe, which at the time was heresy, but of course he was correct. And he used mathematics to understand that it was not really reasonable to think that the Earth was at the center of the universe. So those mathematics combined with observations. Over the last few hundred years, we've become more formalized in describing what we observe in mathematical equations. Right, we model the observed phenomena. We take mathematics and we encompass them in things like Newton's laws of motion, Kepler's laws, which described what Copernicus was seeing, Maxwell's equations for electricity and magnetism, Bernoulli's equations for flow, Black-Scholes equation for mathematical risk, and the relationship in financial services between risk and reward. So we can take those things that we observe, and then we can quantify them mathematically. And over the last few hundred years, we've focused a lot on sort of these mathematical equations for describing what we observe. And then in the third phase, the last half of the previous millennium, we started using computational discovery. Right? We started using high-speed computers to simulate complex phenomena. So we take those mathematical models and we would program them into computational facilities, and we would use advanced techniques like Monte Carlo simulation and the ability to model random interactions found in the real world, and these simulation techniques we use for weather prediction and financial marketplaces and particle and cell codes and hydrodynamics. The picture that you see in front of you here, the computer on the left-hand side, is a Cray 1 supercomputer. That's the first computer that I ever programmed for money. I did this at Lawrence Livermore National Laboratory in the US, and we were understanding hydrodynamic properties of fluids through this computational discovery. The mathematical algorithms could be computed very, very quickly, at least relative to other computers at the time, using this high-speed supercomputer. And certainly more than you could do with mathematical equation with manual solving techniques, which we were doing previous to the advent and proliferation of high-speed computation. But now we are entering the fourth stage, what Jim Gray calls the fourth dimension of analytics. We're in an age where sensor technologies combined with massively parallel processing and cloud computing allows us to measure basically any phenomena and capture those events. And with the advanced instrumentation, we can basically track everything. And we can do it in real time or near real time. That includes, refrigerating temperature in a fast food restaurant like a McDonald's, to patient vital signs in a hospital, or even when patients are at home with the devices that you can use for tracking lots of vital signs for the individual in manufacturing plants. And this data is captured into databases and analyzed in detail with a wide range of slice and dice and statistical techniques, visualization techniques. And Jim Gray, who did a lot of research, he did his PhD at UC Berkeley, which is where I did my undergraduate as well. He went on to teach at Stanford, which is where I first met him. And then he ended his career at Microsoft Research. And he did amazing things, not just thinking about computation, but collaborating with scientists and commercial people to put into real use these advanced technologies. So the vocabulary word that I want you to walk away from this presentation on is SPIME, right? So the SPIME is an object that is aware of space and time. And this was first described in science fiction writing many decades ago, but the science fiction is now science reality. We have a real world phenomena where we can essentially instrument objects and we can track their location with GPS positioning. These objects have memory, they have communication infrastructure. And so every object, and I'm talking about inanimate objects like automobiles and manufacturing machines. I'm also talking about animate objects. Cats and dogs are now instrumented. Humans, we can track humans. If you're carrying a cell phone, you are a SPIME because we can track your location wherever you are. And of course, that's a little bit scary. And GDPR, the general regulation, all of this is absolutely possible using technology that's available today. So science fiction is now science reality. So in the world of big data, there's this evolution that's taken place, right? So the first generation of big data was largely weblog data. So people clicking on websites so we can understand their preferences and what information they're looking at, and the ability to analyze that data allowed us to build recommendation engines and to help users navigate to the right places on web pages and so on, and really understand behaviors of individuals. And then in Web 2.0, social media exploded, and you could start analyzing from Facebook and YouTube and Twitter and Instagram and TikTok, and all these social media applications provided this very rich and often quite unstructured data. But this next phase of the big data evolution, the one that we're in now, is the one that really excites me. SPIMEs, sensors everywhere. This will be orders of magnitude more data than the previous generations. There are not enough monkeys on keyboards using Facebook to generate the volume of data that will be captured as we deploy sensors on every object, animate objects as well as inanimate objects, to drive the next generation of big data capture. So that big data capture is going to drive us, into the zettabytes range. So, here we are in 2021. At the end of 2021, we have, lots and lots of data, again measured in zettabytes. So a zettabyte is 21 zeros. So a zettabyte is 1,000 exabytes. It's a lot of data. And in the previous age, largely we were in what I would call the exabyte age, where it was mainly the capture of transactions. So transactions, anything you bought something at a retailer, anytime you would do a banking deposit or withdrawal, anytime you make a phone call, these are all transactions. And we created exabytes of data in the exabyte age. In the zettabyte age, we go below the level of transactions to the interactions. So the sensors are capturing all kinds of data, not just that the machine manufactured a product, but the temperature and the vibration and the quality and all these measurements we take with the machines, or the interactions, all of the clicks that you're making on the website. Again, that was the first generation of big data, but the generation we're in now is really automated data capture. So it's not humans that are driving the data. It is monitoring of machines as well as living entities to capture data on a continuous basis in real time. We've created more data in the last 3 years than all previous 40,000 years of human history. And that's obviously a lot of data. The total data doubles roughly every 2 years. So we have to have a strategy for dealing with all that data, for creating value from that data. So let's talk a little bit about scale. I first want to talk about scale at a nanometer level, right? If you look at things in nature, right, there are very, very small things. An atom of a silicon is tenths of a nanometer. If we look at the spacing between them, if we look at the things that humans create, at the center of technology is a transistor. At least in today's world. In quantum computing, we're going to change all the rules. But in today's world, a transistor, we have taken transistors and we made them smaller and smaller, cheaper and cheaper and cheaper, faster and faster, right? Less and less expensive means we can create more devices at a lower cost. Right now, the current state of the art in transistor technology is about 6 nanometers. Moore's law basically tells us that every 18 months, we expect to reduce the size of the transistor by about 50% to drive all these advantages in lower cost and higher performance and so on. But there's a limit to Moore's law. In fact, there's a corollary that Gordon Moore talked about. No exponential improvement can go on forever. We are reaching the limits of Moore's law. We just can't make things smaller anymore. And as we make them smaller and faster, it becomes a problem to get rid of all the heat generated. And so instead of making things smaller and smaller, we also think about scale out. So the cloud is really about scale out, not making a single device smaller and smaller. But these small devices are also very powerful in helping us get to the next level of computation. Right? So if we think about, Moore's law and what Moore's law has delivered to us, we get 100x improvement in technology every decade, right? Now the question is, how do we use those improvements? We can take the same function, make it 100 times cheaper. So, going from mainframes to massively parallel processing to cloud computing, we make the compute at scale 100 times cheaper. And of course, this is amazing for being able to handle more data without spending more cost, because the data can be handled in this technology. But we also have to be aware that the data is growing faster than the technology is getting cheaper, so we have to be smart about how we use the data. At the same time, we can create more function and performance for the same price, right? And so, at a lower price, deliver new functionality. And the example I like to use is your mobile device. Your iPhone is more powerful than all of the computers that took a warehouse to store them all, that put the first man on the moon when NASA deployed all the computation necessary to do that space flight. And today, you can fit that warehouse full of computation in your pocket with your cell phone. So there are lots of interesting things that we can do with these technology choices that are afforded to us by this technology improvement. So that personal supercomputer that you have in your pocket, which we call a cell phone, it is capable of computer vision, speech recognition, speech synthesis. You're talking to your phone all the time and asking, Siri or Alexa or Google to do things for you. And this is really inconceivable even 20 years ago, that you could fit all that computation in your pocket. Well, maybe a futurist would see that, but certainly you couldn't do it at the time. You will have a personal petabyte of storage in your pocket. We're not there yet, but we will get there, right? So this is 100 times more powerful, the same price, and the personal computer is an example of that. But I want to go a different direction. The same function for 100 times less cost and much smaller in size. And I'm going to use sensor technology as an example of this. So think of sensors as smart dust. These sensors are microscopically small, and they cost less than a jelly bean. Very inexpensive to deploy, completely self-contained. So these are millimeter scale sensing, and they have their own wireless communication infrastructure. They have their own computational capability. They have the ability to store, and so amazingly powerful thing in these microscopically small devices. So these are basically the size of a grain of sand, costing less than a jelly bean, and it's basically a full-fledged computer. So these sensors, because they're so cheap, we can use them to collect information for all kinds of interesting uses. So as I mentioned, I'm from Silicon Valley originally, and people think of Silicon Valley as the center of a lot of the innovation and technology and so on. And yes, that's certainly something we do a lot of, is technical innovation. But there's another valley that is north of Silicon Valley, called Napa Valley. And this is even more important innovation. This is innovation related to winemaking. So pretty much all the best wines within the United States come from this small region, Napa Valley, which is just north of Silicon Valley. And because of the proximity of these two valleys, they start to have synergies. And so smart dust, these sensors, are being used in Napa Valley on the vineyards, or in the plants that are growing the grapes, to monitor the temperature, the humidity, and all these things, to know what is exactly the precise right time to pick those grapes for the optimal wine. So we're using the technology, the sensor technology, to deliver better wine. What could be more important than that, right? And this is just one example of using sensor technology. People talk about the Internet of Things. I've sort of been describing the Internet of Things. I actually refer to it as the Internet of Everything, because everything will be there. We will move from about 10 billion connected things today to over 25 billion by 2025. Every item on a store shelf, every part in the supply chain, every building, every bridge, every home, every office, every plot of land, every plant, including all those grapevines in Silicon Valley, every machine, every device, everything, every car, every train, every plane, every cat, every dog, every child, right? In Hong Kong, children will wear these, basically a wristband, and it tracks their location. So if you are the parent of a child in Hong Kong and your kid isn't home yet, you just go online and say, hey, where's my child? Oh, okay, Johnny is in the park playing. That's fine. And so we can track. If in the U.S., we love our cats and dogs, and so people chip their pets, and we can track the location of those pets. Everything is measured. You see in the picture here is a sensor where the red arrow is pointing to the sensor in the picture in the right side of this slide. And that picture is actually a picture of a poker chip, right? So you can see that little dot in the poker chip. That is a sensor. So why would you have a sensor in a poker chip? Again, Internet of Everything means everything is going to be tracked. So if we have the chip, the sensor in the poker chip, we can now see how people are betting, and we can see if they're counting cards. And of course, we don't like it if they count cards, so we will ask them to leave our casino. We can also use the observations of how the chips are being played and how money is being passed between people on a poker table to see if gambling is being used for money laundering. So there are all kinds of applications of the sensor technology that you might not think about just on your own. And I'm going to introduce some other uses of this technology, right? But I want you to think of this Internet of Everything as a huge impact, this connective mesh that allows you to collect data and the whole ecosystem and combine that data. And think of the science fiction idea of the spine that I described earlier, and think of how a hive of bees operates, or a colony of ants operate, where through all of these entities collecting data and sharing data, they get this mind-blowing state of total awareness, and do amazing things that one individual can't do. And we can apply that to living things like bees and ants, and then extrapolate that to humans. And then we can also think about a network collection of machines also working together in this connective mesh. And of course, this relates to advanced uses of algorithms and machine learning and deep learning. AI is an important part of this capability, right? So as we deploy this in the real world, we can do basic things like every product can self-report usage characteristics. So for example, if you instrument your vehicle, and this is already done in Tesla vehicles and in Volvo vehicles and in a number of other manufacturers, you use the sensor technology to measure how is the car being driven. And is the car behaving well? Is the car overheating? Is there too much vibration? And I can essentially with this self-reporting, I can monitor when is the right time to take the car in for service. Because in the past, service was based on, after you drive the car for 20,000 kilometers, then bring it in for a checkup. But 20,000 kilometers is just an average number calculated by some engineer that says, well, after 20,000 miles, we should see the car. But it really depends on how you drive the car, right? So, my brother, he drives a car. He drives very quickly. He uses the brakes a lot. He kind of abuses his car. He needs to bring his car more often. But someone who drives their car very nicely, they can bring in the car less often. In fact, the milestone-based maintenance on most machines, whether it's a vehicle or it's a machine in a manufacturing plant, you're typically doing between 30 and 50% more maintenance than required, because the milestone-based maintenance triggers are very conservative. So you can actually save a lot of money by doing condition-based maintenance instead of milestone-based maintenance, right? And so the self-reporting helps each machine be able to report when they need service or how they're being used. And by the way, I say machine, we can have wearable sensors for humans, and humans can also be reported on that if they have a temperature or if they have high blood pressure and so on. We can monitor these things, high blood sugar level, they can self-report, and then we can intervene with maintenance, like going to a doctor or taking your medicine. So very interesting things going on. And then you can also do things like external control. You can remotely influence the behavior of smart devices. So if you have machines on a manufacturing line and the machine is misbehaving in some way, you can maybe make some adjustments through software and machine learning algorithms completely automatically, right? So we can control and optimize for more efficient use. And eventually what's going to happen is that these devices will be deployed with self-learning capability. You already see that in Tesla cars, right? So you get new upgrades of software. So when you upgrade your vehicle, you're really doing a software upgrade. The software upgrade has more sophisticated algorithms to do a better job of self-driving, a better job of parking, a better job of maintenance, whatever those things are. And interestingly, Tesla cars come with warranty for life, because they're so confident about the ability to sort of monitor and do this condition-based maintenance that they can include that as a service. When you buy a Tesla car, you're actually essentially buying software. Yes, of course, there's steel and rubber and so on that goes into the manufacturing of the car, but most of the intellectual property is in the battery technology and in the software technology. Those are the two places where the most innovation is taken place in this new generation of vehicles. So, how we're evolving is to this concept, which is called a digital twin. A digital twin is basically a software replication of the physical asset. So if you're driving a vehicle, we can basically have a software simulation of the vehicle, right? And so all of the components of the asset are modeled in software, and then the dynamics of how the assets operate are captured in the software, and there's simulations that can predict what's going to happen before it even happens by understanding how the machine is being used and what the trends are in terms of something that is maybe going to break in the next 48 hours or next 4 hours. And I talk about this in the context of machines like vehicles, but now it's expanding to systems of systems. So now smart buildings, smart cities, telecommunications networks, even human body, or in agriculture, farm crops, we can model these things using software replication of the physical asset. And physical asset is, it could be a living thing, a stalk of corn or a vine of grapes in the farm, and we can start monitoring these with the sensor technologies and be proactive about intervention to improve our processes and execute much more efficiently. Right, so we talked a lot in the last decade or 2 decades about digitization. That's basically taking assets from physical into digital, and of course we've already seen that in books and music and customer service chatbots and self-service airline bookings. These things have all gone digital. That's really going from assets and experiences in the physical world to one in the digital world. We can also go the opposite direction. We can go from printing digital designs into real world objects. That was the innovation of 3D printing, right? So this is an incredible transformation from digital to real world. So we can go both ways. We can take physical things and digitize them, or we can take digital things and physicalize them. Digital twins takes this concept one step further by linking the worlds of atoms and bits on a real-time basis through digital software copies of the physical object that coexist in time with real-time feeds for sensors, so you can understand what's happening with these objects as they're behaving in the real world, and what's going to happen in the future through these advanced simulation and machine learning techniques. So it's a very, very interesting evolution to these digital twins. And this concept has been around for at least coming on 20 years, but the concept is now becoming reality because of the widespread use of IoT technology, the Internet of Things, for enabling cost-effective deployment of these sensors, and collecting all that data is enabling digital twins. So Gartner made a prediction that in the next 5 years, 85% of IoT platforms will be coupled together with digital twin technology. So we can connect the software world with the physical world. And the predictions are that the productivity gains will be upwards of 25% to drive value for businesses. So these digital twins can predict and even create new outcomes for a machine or a farm or a human using these advanced machine learning algorithms, with the data from these sensors being the fuel for those algorithms. So almost 50% of organizations who are already deploying IoT capability said that they are also using digital twin technology, or they will use it in the next 12 months. So this is clearly happening in our world, and this digital twin technology, again, is enabled by these sensors. So think of the digital twin as a proxy to the real world object, right? It's a software, virtual twin, right? And it's the sensors that are embedded in the physical world that are the connection between the physical asset and the software version of it. So they communicate by delivering the data captured by the sensors on a continuous near real-time basis into the software asset. Now, once you have the software asset in place, then you can use that data to start doing prediction of things even before they happen. So now you have this ecosystem of digital twins all interconnected. They're like mirror images of the physical things, people and buildings and machines and so on, and then we can model their interactions. And of course, we have to walk before we run. We'll start with individual machines, and then we'll evolve from, understanding individual machines to collections of machines and systems and so on. We become increasingly sophisticated over time. So if we look at the life stages of a digital twin, there are basically four pieces of it, right? So the first is, create a software replication of the asset as designed, right? So if I have an airplane, I've got a bill of materials for everything that went into the manufacturing of that airplane, right? What are all the parts? I have planes, I have airplane wings, I have the seats in the airplane, the cargo. I have a complete specification of that plane, and I'm going to translate that specification into a software version of the plane. That's the design part, and there's basically one design for all of my planes. But the reality, as I design individual planes, the build will drive, slight differences in the supplier for this particular instance might be different than the supplier of for a different instance of the plane. So it's the same design, but the specific parts and materials may be different because there are multiple suppliers and manufacturing in different places and so on. And there might be engineering changes to the original design that are part of the build process. We capture that in the software. Then in the deploy, we look at, okay, what is the route that this plane is flying, right? So it's very different if the plane is in, let's say, the Middle East, where there's a lot of sand and there's a lot of heat, versus in Russia, where there's a lot of cold and completely different conditions. And so we need to understand, how the asset is deployed, including all the environmental conditions. And then we need to understand how it's being operated. So now the sensor data is, feeding in real time as the asset is being operated, and we understand how to monitor it and do diagnostics and so on. So there are kind of 4 life cycle stages of building and deploying digital twin technology. Right, so here's an example that is related to my home state in California. So most of you, if you've been to California and you travel between Northern California, like San Francisco, to, let's say, Southern California, like Los Angeles or San Diego, you probably took what's called the PCH, the Pacific Coast Highway. This is the road that all the tourists take because there's beautiful views of the ocean and Big Sur and so on. Beautiful, beautiful drive. And if you haven't done that, I would recommend that you do it. But the locals, the people that live in California, they don't want to drive behind all the tourists. They go down Highway 5, which goes down the middle of California. And I will tell you, the reason the tourists don't take that drive is because it's very boring. You will only see 2 things on that drive. You will see cows, and you will see windmills or turbines that I'm showing here. And so these wind parks are all, through the middle of California to capture wind energy and convert it to electricity that we can use to consume power for all this innovation we're doing in Silicon Valley. So the implementation of this comes with digital twins. So for each one of these turbines, there's a digital twin that is monitoring the energy being produced, the velocity of the blades, the wind direction, the vibration, the temperature, everything. And there's software that is used to control how much energy is being produced. So for example, if we are in the middle of the day when we need extra energy, we may push the windmills a little bit harder and make the turbines turn faster. Now, the faster we turn them, the more vibration that we cause. That requires more maintenance to be done. So we don't want to push them too far. But if we're peaking out, we may choose during certain times of day to create a higher maintenance burden in exchange for a better energy generation. During low periods of energy usage, we wouldn't do that because we don't want the cost of the extra maintenance. So not only do we have these sensors collecting the data about the environment and helping to understand how to optimize maintenance and so on, you also look at the economics. How much energy do we need? How much energy demand do we forecast? How much can we store from these turbines? And how much faster should we run the turbines in order to collect more energy so then we can distribute it to people who need it? So digital twins is sitting behind as a software mirroring of each one of these turbines, and it's used with lots of machine learning and deep learning in order to understand how to optimize the operation of these devices. And so if something as boring as windmills is using this software technology of digital twins, you can imagine every vehicle and the machine and a manufacturing plant and so on is definitely doing it as well, and has been doing it for quite some time. So with a digital twin, you can start to you can interact with a digital twin. You can ask it, how are you feeling? Are you going to break soon, right? And the predictive models will help you understand that. How much fuel is left? How much power are you consuming? Temperature, all of these things. And I'm talking about machines, but also humans, right? So how are you feeling? How is your temperature? When was the last time you were at the doctor? Which is kind of the same as the last maintenance. And when should be your next maintenance? And so we can create dashboards on top of the digital twins, and those dashboards will eventually evolve into much more sophisticated simulation and predictive and prescriptive analytics. So the dashboards are really descriptive analytics, understanding what happened in the past, what's happening right now. Predictive analytics is what's going to happen next, right? So this is where the machine learning and the deep learning, the AI algorithms come in to understand what's going to happen before it happens, and then to prescribe an intervention to make sure that you create optimal outcomes. And so the software interaction with the digital twins is going to evolve over time as we get more sophisticated with these machine learning algorithms. And smart cities is a good example of system of systems, where we use this digital twinning technology related to how we light the city, how we deliver transportation through buses and subways and so on. Everything is being instrumented. Siemens did an amazing implementation with digital twins and sensor technology for the train system in Spain. So they called IoT is Internet of Trains. So all the trains are sensor enabled, and they made commitments to the Spanish people about the service levels of these trains and so on. And they far exceeded these because they had the data in their hands to understand how to optimize on a continuous near real-time basis, right? And like San Francisco, where I'm from, people when they drive from A to B, they spend more time parking once they get there than the time it took to drive from A to B. And so smart parking actually uses sensors to monitor where are the open parking spots and so on, and to take you immediately to the open parking spots rather than have people driving around and so on. So there are some very simple things that we can do with sensors. So digital twin for each parking spot. It's a very simple digital twin that understands, how much money it's collecting and whether the parking spot is open or closed and so on. But these things will evolve into more sophisticated analytic capability to understand, and forecast how much parking do we need, and maybe there will be differentiated pricing depending on time of day and so on. So these smart city implementations using sensors are starting to proliferate in different parts of Europe and the US and so on. So there's a whole bunch of startups that are evolving from these capabilities, and new jobs are being created, and lots of interesting things happening in this space. So that's all great news, but there's some maybe less encouraging news. Studies by McKinsey show that less than 1% of the data collecting from sensor instrumentation is actually being used for analytic purposes. So we're collecting lots of data, right? And data is an asset. We want to collect more of it because data has value. But if you don't use the data, it doesn't have value, it just has cost, right? And so simple event detection is relatively unsophisticated when using rules engine to detect when a machine is down or something like that. Okay, it's a starting point, but we really need to think about best practices where the digital twin technology is not only for creating dashboards and alerts, but to be able to predict and optimize with interventions using prescriptive analytics and artificial intelligence techniques to create better outcomes. And this is the challenge that we have for data scientists in using all the sensor data that we've been collecting. Now, in the last 20 years, the majority of the beneficiaries for big data have been B2C enterprises. So, people,